Yeah, so let's start basically. Anyone who would like to define a graph for me? Okay, so somebody is saying that graphs is a set of nodes and vertices. Sounds very apparent, right? So basically he's saying that there will be a set of nodes and then there will be a set of vertices. So basically node and vertices both are the same words. So I believe your intention would have been set of edges and vertices. So there will be a set containing edges and there will be another set containing vertices. So this makes sense. There are certain edges and there are certain vertices. So I think all of you have already studied about trees, right? Everyone knows what is a tree and how to represent that, what are the components inside a tree. So even a tree has a set of edges and a set of vertices. So no matter what tree you are looking at, let's say you have 1, 2, 3, 4, 5, 6. Yeah. Here also I can say that 1, 2, 3, 4, 5, 6, these are my vertices, and 1, 2 is an edge, 1, 6 is another edge, 2, 4, 2, 3 and 4, 5 are many different edges out there, right? So can I say that from that definition tree is also a graph? Can I say that? I can actually say that, right? Because the best possible definition for graph is just this only, that it is a set of edges and vertices. So what kind of graph is a tree? I mean, you're saying that tree is also a graph, so what kind of graph? In fact, one of you mentioned it, so it is an acyclic graph. Yeah. So I think when I was discussing about trees, then I talked about this thing that in trees there will not be any cycle. So now when I say that there will not be any cycle, it is basically an acyclic graph. And now in tree, if you pick any two nodes, let's say you are picking 4 and 6, you pick any two nodes n1 and n2, then how many paths will be there connecting n1 and n2? There will just be one path, right? Like here I can say that this is the path which takes me from 4 to 6. It will never so happen that there are more than one path connecting two different nodes. It will never ever happen, because the moment it happens, then a cycle is going to get formed, right? And why is that going to get formed? Let's take an example. So let's say there was any other path also connecting 4 to 6. Let's say it was this. So you can go from 4 to 2 and 2 to 6. Now you can see that this is cyclic. In fact, this is normal, right? So if there is a node n1 and there is node n2 somewhere else, and let's say there are some connections through which you can reach from n1 to n2. So let's say this is one path. Now if somebody says that there is another path, that could be something like this getting connected to this, so you go from here to here, here to here, and then here to here. Now again, this thing that you see, it has become a cycle, right? So this is a very, very interesting property in a data structure, having a cycle. So the moment you are able to conclude that between two different nodes there are more than one paths, so you can say that definitely that data structure will have some kind of cycle in it. Cool. So I think this is the best possible definition of graph, where you can say that it has certain edges and it has certain vertices, right? So let's take a very simple graph. Let's say I have this, B is connected to C, right? Now here I can say that this is a graph which contains two vertices and one edge. Okay. Now if I talk about the set of vertices for this, the set of vertices will contain B followed by C, and set of edges will contain some information that will denote a linkage between B and C. Okay. Now if I try to understand this graph very carefully, there are a few important technologies that all of us should be very, very clear at before we move into further topics. So first thing is that this edge over here, which kind of edge it is? So is it a directed edge or it is an undirected edge? So I think some of you might have heard about what do these things mean. So this is an undirected edge. What is the meaning of undirected edge? So undirected edge means that if I can go from B to C, I can also go from C to B. So this is called as undirected edge. So it is basically a kind of relationship between the two things which are being connected. Okay, so for example, if you can go from Delhi to Indore, then you can also go from Indore to Delhi, right? So such kind of relationship is called as, such kind of edge is called as an undirected edge. And basically an edge is nothing. An edge is a relationship between the two nodes which it is connecting. I repeat it again. Edge is a relationship. It is a mathematical relationship between the two nodes which it is connecting. So if the two nodes being connected are, let's say, places on the earth, then the edge can denote a distance. It can denote something like that, right? So now when it denotes distance, this becomes very, very apparent to my mind that the distance between Delhi and Indore will be different from distance between Delhi and Hyderabad, right? So if this distance is, let's say, 50, this distance would be something like maybe 70 or 90, something like that. So such kind of cases where different edges represent different mathematical things or different mathematical quantities, that is called as weighted edge. Okay, so weighted edge means, just take out the word weight from here, that every edge has a weight associated with it. So this has a weight of 70, this has a weight of 50, and so on and on and on, right? And until unless specified, you have to assume that the edges are unweighted. Okay, so again, this is one categorization of edge, which categorization is basically with respect to directions, which calls for the fact that it can either be directed or undirected. And second categorization is with respect to weights. So it can either be weighted or it can be unweighted. So you can take an example of a weighted of a directed graph also. So let's say you have A connected to B, connected to C, and like this. So here there is an edge between A to C. I can say that I can easily go from A to C like this also and like this also. But can you tell me if I can go from C to A? I cannot go from C to A, right? There is an edge between A and C. I can go from A to C, but I cannot come back from C to A. Similarly, I can go from B to C, but can I go from C to B? No, I cannot go from C to B via the same edge. So such kind of cases are the cases of directed edges. Cool. So directed edge technically just means that there is a relationship between node 1 and node 2, but that relationship will not be there for node 2 and node 1 as well, right? But in undirected edge, that is not the case. Weighted, you all understand what is the meaning of weighted. Okay, cool. Now, the graph that you have. So basically, when we study graph, it comes to our mind that, hey, every node will be having some label, maybe 1, 2, 3, 4, something like that. But in real world, that is not the case. You can create a graph of anything. Okay, I'm just trying to give you an example. So I can create a graph where every node can be a bit string. Every node can be a bit string of size, let's say 3. Okay, so I have a node which contains a bit string 001, and I have another node which contains a bit string 101. Okay, and now the edge can denote Hamming distance between bit string 1 and bit string 2. What is the Hamming distance between 001 and 101 over here? So the Hamming distance between two bit strings are that if I have a bit string like this and another bit string like this, then the Hamming distance between two bit strings means that at how many bit positions the values are different. So at this bit position values are different, here also different, and here also different. So the Hamming distance as calculated for this versus this is equals to 3. Right? So here it can have a weight which is equal to the Hamming distance, which I think is 0 and 1 are different, 0 and 0 are same, 1 and 1 are same, so the Hamming distance is 1. Now let's say you are making such a kind of graph where the nodes are bit strings of same size and the edge represents the Hamming distance. will the edge be a directed edge or will it be undirected edge according to you? It will be clearly undirected edge. Why? Because if the Hamming distance between this and this is 1, then Hamming distance between this and this will also be 1. So depending upon the nature of the problem that you have, you will be able to understand it very, very clearly that the graph that you have to frame in your mind first should be a directed graph or should be undirected graph. Okay. So another important point that I am calling over here, that your node can literally be anything. Okay. Okay. Like it can also go to this extent, something like this, that let's say there is a word book, and then there is another word called as maybe bold. Okay, something like this. Okay. So there is a very, very popular distance that is called as edit distance or Levenshtein distance. So edit distance basically means that if I have to convert word 1 to word 2, then how many changes should I do? Changes could be like adding a new character, deleting a character, or replacing a character by another character. I repeat, changes could be adding a new character, deleting an existing character, or replacing a character by some other character. So in this case, I can replace K by D and O by L, and then I can get bold from this book, right? So I can say that the edit distance between this and this is 2. And again, you can say that, hey, the edit distance between this and this also looks like it is 2, right? So your node could literally be just anything. Certain times what can happen is that somebody is giving you a problem where he is saying that, let's say there is a dictionary, okay, and in that dictionary there are many, many different words, okay, and now he is saying that, hey, 2 words are directly connected if there is just a difference of 1 character between them, okay. So 2 words are directly connected if there is a difference of 1 character only. So from this, what I mean to say that if I have a word called as book and another word called as took, then I can say that, hey, these 2 will be directly connected to each other. Why they will be directly connected to each other is because at just 1 character they are having different values, remaining everything is same. So you can say that book is directly connected to took, and took is also directly connected to this. And now again you can say that, hey, this is directly connected to maybe something like tool, and tool is directly connected to toil, right? But you can say that book is not directly connected to tool because book and tool are having differences at 2 distinct characters. Book and toil are also not connected. So basically, this is a game of connections, and this game of connections is derived from the nature of the problem. So if the problem basically explicitly tells you that connection will be there between 2 things only if there is a distance of, let's say, 1 or maybe something else, then your graph is to be created in that manner. And graph needs not be graph of just labels. It can be graph of strings, it can be graph of anything. You have to use your intelligence to convert a problem, to model a problem into a graph problem, which we will be doing throughout. Okay, in the meantime, can someone talk about some well-known systems, well-known softwares, websites that you use and you think that it might be using graphs inside it? Facebook is a very clear example, right? So what happens in a Facebook? So let's say there is a boy B1 and he is friends with a girl G1. Let's say that is the case, okay? Then which kind of connection is this? On a Facebook, friends relationship is denoted by a edge, and every node is a person. Every node is a Facebook account, and every edge talks about the fact that these 2 accounts are friends of each other. So which kind of edge it should be? Should it be directed or undirected? It should be undirected, because if A is friends with B, then B is also friends with A, right? So Facebook graph of friends, from the perspective of direction, it is undirected graph, right? So this is an a very well known example. And again, like you might have heard of things like 2-degree connection or 3-degree connection on LinkedIn or on Facebook. How many of you have heard of these terms? 2-degree, 3-degree connections. So what do they mean, right? So it means that this guy, let's say it is a case of just Facebook. Okay, so I can say that, hey, this guy is my direct friend. Okay, but I can call that this guy, let's say G1 is friend with another V1, then he is not my direct friend, he's friend of friend. So maybe I can say that, hey, this guy is my 2-degree friend and this guy is my 1-degree friend. Okay, but if let's say I was also friend with this guy, then it would have meant that, hey, this is also my 1-degree friend and this is also my 1-degree friend. Okay, so that is how they come up with these kind of terminologies. And mutual friends also, now you can envision what do mutual friends mean. So let's say there is a boy B1 and there is a boy B2, and they are friends with X, and let's say X is friends with Y and also friends with Z. Now you can say that X is a mutual friend of B1 and Z also. It means that if you talk about B1 and Z, then they both are not connected to each other, but its friend is also X and its friend is also X. So it's like that graph is in action over here, right? Without using graphs, you cannot figure out such things. Okay. Anyone can give me an example of a well-known social media network where such kind of relationship exists, but the graph is a directed graph. So it is the use case of following someone. So let's say you are using Twitter. If you use Twitter, if let's say you are X, and let's say you follow Amitabh Bachchan, for example, then it doesn't necessarily mean that Amitabh Bachchan will also follow you, right? So such kind of relationship is basically a directed relationship which exists on Twitter, which also exists on something like Instagram. Okay. On LinkedIn also there is this feature that you have. So you can follow someone, you can follow, for example, Jeff Bezos, but that will not mean that Jeff Bezos also needs to follow you. Okay. System will not assume it that Jeff Bezos follows you unless he explicitly does that. Okay. Okay. So if let's say there is a tree of n nodes. So there is a tree of n nodes. How many edges would it contain? It would contain exactly n-1 edges. Okay. And why is that the case? Because let me tell you, if there are 4 points. If there are 4 points and I connect them in a linear fashion, okay, then there will be 3 edges coming up. Now this thing is also a tree, right? I mean, this is a skewed tree where you can envision that this is your root and this is how the tree looks like. Okay, and now you can restructure this tree by maybe moving it from here to here, or maybe moving it from here to here, and then you can create all the possible different variations of trees that are out there, right? But if you think of any other kind of edge, if you introduce any other extra edge inside this, then what will happen over here? Don't look at here, just look at here. If you create any other edge over here, then it will lead to a cycle. If you connect this and this, then also a cycle. So from here I can intuitively see that till n-1 edges, no cycle, right? But the moment you introduce even one extra edge, then there will be a cycle for sure, right? So if there is a cyclic graph, then the number of edges will definitely be greater than or equal to n. Okay, so that is an important thing. Now tell me, if you have a graph with n vertices, so there is a graph with n vertices, what is the maximum number of edges that it can have? Yeah, you can assume that it is undirected for now. Let's say it is undirected. What is the maximum number of edges? Yeah, it will be basically n into n-1 by 2. NC2 is the most correct answer. Why? Because if let's say I give you 4 different nodes, then basically what you would want is that in the worst case you would want that every node should be connected to every other node. Okay, So it's like connecting all the two nodes from n different nodes. Okay, so you can say that it is just a matter of picking two nodes and then connecting them, right? So when I say that, let's say you have connected node 1 and node 2. After this, you would not want to again connect node 2 and node 1, right? Because this is an undirected edge, right? So even if you do that, then it will be like a parallel edge which is redundant. So all that I have to do is I have to figure out in how many ways I can pick two nodes and draw an edge in between them. So how many ways are there to do that? NC2 ways are there to do that, and NC2 will be n into n minus 1 by 2. So you can see here that in case of 4C2 is 6, and you cannot think of, I mean, it would be redundant to consider any other edge. Okay, so NC2 is the maximum number of edges that can be there in such kind of graph. You can call it as something like completely connected graph, maybe, where every two nodes are directly connected to each other. Now this is a very subtle but important word, directly connected. Directly connected is different from connected. See, even if let's say this is the case, and let's say the nodes are A, B, C, D, can I say that A and C are connected to each other? Yes or no? I can say, right? Because if I start my journey from A, I can go from A to B and B to C. Similarly, I can go from A to D and D to C, right? No one stops me from doing that. But they are not directly connected. Here they are all directly connected. So a completely connected graph can be thought of as that graph in which all the two nodes are directly connected to each other. And it will have NC2 different edges. This is a very important point. So let us just think of whenever we try to solve a graph problem, then that graph problem's nature might become different if you think about undirected edges, and it might again become different if you talk about directed edges. Okay, so you have to be very, very clear that what exactly you are talking about. Okay, so for now, let's say I will talk about undirected graph. So let's say there is an undirected graph where you have A, B, C, D, and then E, F. Okay, wait, before I move ahead on this thing, I would say one more thing. So let's say you have 3 nodes, then the maximum number of edges that you can draw is 3 edges. Now sometimes people, what they do is that they say that there can be an edge like this also, or there can be an edge like this also. No one is stopping you from doing that. You can do that, but see, this kind of thing is called as a self loop. Okay, and we are not going to be talking about self loops for now. Self loops in any ways are redundant, right? So until unless problem says that there is a graph containing a self loop, please do not assume on your own that there might be self loops also. Okay, so this is a rare kind of input that you have sometimes, that it has self loops and then you have to solve it. And then certain times there can be some parallel edges. Okay, so you don't have to worry about that also for at least a very long time. Okay, so do not worry about these cases of self loops and these cases of parallel edges. So now if you take a look at this graph, in such a kind of graph, let's say I pick any node 1 and any node 2. Let's say node 1 is F and node 2 is C. For any node 1 and any node 2, can I say that always I can reach from node 1 to node 2? Yes or no? Just pick any 2 nodes from here on your own. So for example, if I have picked F and C, I can say that I can go from F to C. I am not talking about number of ways to perform this journey. I am just talking in terms of booleans, whether or not you can go from n1 to n2 or not. So all that I can say is that if I pick any 2 nodes, then there is at least one path linking node 1 to node 2 and node 2 to node 1 also, right? So such a kind of graph where for any 2 nodes there is at least one path is called as a connected graph. So this is a connected graph. Certain times what can happen is, everyone got what is connected graph, right? For any 2 nodes there is at least one path. Certain times what can happen is, if you forget about this thing, and let's say I take this, tell me one thing, is this entire thing a one graph or not? It is, right? It is. So I'm just going to give you an example. So entire Google Maps is one graph, right? So let's say Google Maps connects cities to cities. Okay. Now it cannot connect a city in India, which is Delhi, to New York. It cannot do that, right? But New York could be connected to Las Vegas and else and else and else, and Delhi can be connected to others, right? So what you can see is that there will be a connected component here and there will be a connected component here, but this entire thing is a one big graph only. This is the same scenario over here, where you can see that if I talk about this subgraph of a graph, so the way you have a subtree in a tree, similarly you have subgraph in a graph. So this subgraph of the entire graph is connected. This subgraph of entire graph is also connected. Why? Because you can go from anywhere to anywhere. Here also anywhere to anywhere. And this subgraph is also connected. This subgraph is also connected. So there are these many connected components in this graph. So if somebody asks me about count of connected components, then I can say that there are 4 connected components in this graph. So what is a connected component? A connected component is that subgraph of a graph where if you choose any 2 nodes, then there is at least one path connecting those 2 nodes. That is called as a connected component of any graph. And you know, such a kind of graph, in its set of vertices, it will have A, B, C, D, E, F, G, H, and in its set of edges, it will have A connected to B, A connected to C, and this connection is undirected, okay? C connected to D, E connected to F. These are the edges that it has, okay? So if let's say a graph has been given to you as an input, okay? Let's say this is the graph, 1 connected to 2 connected. Yeah. Let's say this is the graph that's given to you, and somebody asks you to check whether this is a connected graph or not. If somebody asks you to check whether this is a connected graph or not, and let's say there is a random function, this function takes in the graph as input and returns the count of connected components in that graph. You do not have to worry about how to implement this function. Don't worry about that. Let's say this is a magical function created by God. It takes in any graph as input and tells you how many connected components are there. So if a graph has been given to you as an input and you have to check whether that is connected or not, can you use this function and figure out whether this graph is connected or not? In a connected graph, how many connected components will be there? If a graph is connected, the number of connected components will just be how much? It will just be 1. Yeah, so this is litmus test for the fact whether a graph is connected or not, right? If you see that number of connected components is just 1, then it implies that that particular graph is a connected graph. And if number of connected components is more than 1, it means that there are some nodes such that one node belongs to component 1 and other node belongs to component 2, which are not reachable from each other, right? So this is the way you check whether a graph is connected or not. We will talk about this function, how to implement it later on. You know, basically sometimes what happens is that let's say I give you a graph like this, A, B, C. Now sometimes, you know, what some people will say is that if I just consider AB which is a subgraph of this connected component, then that AB can also be thought of as a connected component. And then they will say that, hey, this AB is one connected component, this CD is another connected component, this EF is another connected component, and then they will say that, hey, for this thing the answer could be 3 also. But that is a stupid thing to do. Why? Because if there are 2 connected components which are somehow connected by each other, then that accounts for 1 connected component only. So never do such kind of stupidity, right? So if that is the case, then I can treat every node as 1 connected component, and then I will say that, hey, if there are V vertices, there will be V connected components, right? So that is not the right thing to do. Did you get what I tried to say? Yes or no? Certain questions will be framed in a way that will try to trick you like that, okay? Just don't fall into that trap. So This was undirected. Now I'm going to give an example of a directed graph. Let's say you have A, B and C. First question, is this graph a connected graph? Yes or no? This is not a connected graph. Why? Because I cannot go from B to A, I cannot go from C to A, I cannot go from C to B and B to C, right? Next question is that how many connected components are there? 3, right? 3 is the perfect answer, because you cannot take any two of them. Let's say you cannot take AC and say that they belong to a connected component, because you can go from A to C, but vice versa is not true. You cannot go from C to A. So all of them have to be treated as, separate connected component. So in case of undirected graph, it might look to you as if it is a connected graph, but it won't really be, because the meaning of directed graphs are entirely different. So this you have to strictly keep in your head. Okay, let's take another example. Let's say you have, anyone who can tell me how many connected components are there in this graph? Yeah, so you can say that, hey, this thing, this ABC is one connected component, because you can go from A to B to C, you can go from C to A to B and so on. And this is also one connected component, and this is another connected component. So there are 3 connected components over here. So this is a very important point, and that makes the process of finding connected components in a directed graph as a different problem than a problem of undirected graph. In undirected graph, the process is simple. Here the process is not that simple. And in undirected graph, these are having a special name. These are not called as connected components. These are called as strongly connected components. So in undirected graph, the connected component is basically called as strongly connected component. That is the only thing that you should understand. Okay, and the same thing in undirected graph is called as connected component. That's it. So there are 3 strongly connected components in this particular graph. Okay.